Hey there. You ever watch something bubble, fizz, or even explode and wonder what's actually going on? It might look like total chaos, but chemistry, it's not random at all. It follows some really fascinating rules, and today we're going to pull back the curtain and see what they are. So let's get right into it. Just look at this. A tiny little piece of potassium metal hits the water and boom! It just erupts into this incredible violet flame. It's so dramatic, right? So intense. But is it magic? Well, no. It's actually a perfectly predictable chemical reaction, and it's following a very clear set of rules. And over the next few minutes, we're going to unpack the simple logic that's behind all these amazing transformations. Okay, let's kick things off with the simplest rule there is. What happens when you just heat something up? This is all about chemical breakups, or what scientists call decomposition. The idea here is actually really straightforward. Thermal decomposition, it's just a fancy term for when a single compound breaks apart into simpler pieces because you heated it. Basically, one thing turns into two or more new things. Let's actually see this in action. We're going to start with this really nice-looking blue powder, which is called copper hydroxide. All we're going to do is put it in a test tube and add a little heat. So what's your guess? What do you think is going to happen to this blue powder? Is it just going to melt, change color, or maybe just get really hot? Think about it for a sec. And there you have it. The blue powder turns into this black stuff. That heat gave it just enough energy to trigger that chemical breakup we were talking about. The copper hydroxide literally split into two simpler things, black copper oxide and some invisible water vapor. A complete transformation just by adding a little heat. All right, so that's what happens when one compound breaks apart. But what happens when you have two different elements competing with each other? This brings us to our next rule, the element swap. And it's all about a sort of chemical pecking order. Okay, look at the difference here. On the left, you put zinc in acid, and it goes crazy, bubbling away and releasing gas. But on the right, you put copper in the exact same acid, and nothing, not a thing happens. This tells us something really important. Not all metals are created equal. Some are just way more reactive. And this isn't random either. It's all governed by a rule book called the Chemical Activity Series. Seriously, you can think of it like a league table for elements. An element that's higher up on the list can literally bump a lower-ranked element out of a compound. Zinc is higher than hydrogen, so it reacts. Copper is lower, so it doesn't. It's as simple as that. And this shot illustrates the whole idea perfectly. Here, we're putting a piece of magnesium, which is ranked super high, it's very active, into this blue copper sulfate solution. The magnesium is stronger, so it just kicks the copper right out and takes its place. And you can see it. The solution turns colorless as the copper metal starts to form. A textbook swap. So, we know a more active element can swap with a less active one. But what if you have two compounds, and they both decide they want to trade partners? Well, that brings us to our next rule, the double substitution dance. The basic idea here is actually beautiful in its simplicity. You've got two compounds, let's call them AB and CD. Just think of each one as a pair of particles hooked together. When they mix, they just elegantly swap partners, forming two brand new pairs, AD and CB. One of the most classic examples of this partner swapping is called neutralization. It's what happens when an acid meets an alkali. They swap their ions and end up producing two totally neutral things, a salt and good old water. But this whole partner swapping thing isn't just about making water. Let's see what happens if we mix some sodium carbonate with hydrochloric acid. And just for fun, we're going to put a balloon over the top of the flask to see if this particular chemical dance creates something we can, catch. And would you look at that, the partner swap, but this time, one of the new things they make is carbon dioxide gas. All that fizzing inside the flask releases enough gas to actually blow up the balloon. It's a direct, totally visible result of that chemical dance. So we've seen compounds break up, and we've seen them swap partners. We know some elements are stronger or more active than others. But why? Why is that? It's finally time to uncover the real secret behind the swap. The electron dance. We keep using this phrase, more active. But what does it really truly mean? What is actually happening down at that tiny atomic level that makes zinc so eager to react while copper just sits there? And here it is. This is the big secret.
It all comes down to electrons. A sodium atom gives away an electron, and a chlorine atom takes it. That simple exchange, that one little electron jumping from one atom to another, is the chemical reaction. An element's reactivity is really just a measure of how badly it wants to give away or grab an electron.
And this electron dance, it always has two parts. The atom that loses the electron, we say it's been oxidized, and the atom that gains that electron, we say it's been reduced. Here's the key part. You can never have one without the other. It is always a single process of giving and taking, together.
So you can think of it like this. The substance that gives away the electron is called the reducing agent, and the one that takes the electron is the oxidizing agent. They are partners in the very same dance. You simply can't have one without the other. And this brings us right back to the beginning, that chemical activity series we talked about. It's not some mysterious list. It's simply a ranking of elements based on how easily they give away their electrons. The guys at the top, like potassium and magnesium, they're just the most generous electron donors around, which is what makes them so reactive.
So there you have it. From simple breakups to the fundamental dance of electrons, all these reactions follow a clear, predictable logic. So now that you know the rules, who breaks up, who swaps partners, and who's the best at giving away electrons, what other chemical mysteries do you think you could solve?